All right, we're going to start by starting with the bare board, and we're going to have a 1K resistor, a 10K resistor, a 2.2K resistor, the diode, the 100 PF cap, and the 2.2 PF cap, which is labeled, you can't see it, can't focus, 222, and the other one's 100 PF. It's got a little black dot on top. Your barrel connector, the coil, the trimmer pot, the 4.7 microfarad 450 volt capacitor, socket for your 555, a 555, your NPN transistor, and the MOSFET. These are the parts that you're going to need initially to get the power supply going, and it's actually the trickiest part. And it's not tricky, it's just that you build this first, and then using your meter, you adjust the trimmer pot till you get to 180 volts, and you're done. And then you can continue to just build the rest of the circuit out. So it'll look, you know, more like this, with all the parts and components on it. I'm going to send you a better schematic than the one that is in the box. But this is step one. So I'm going to start on this MOSFET. Isn't 740. It's going to go here. There you go. The 4.7 cap, the 100 UH coil, the 2.2 or 2N2. I should have done this first. Ceramic cap. A little itty bitty 100 picofarad that attaches to the MOSFET right there. The 2200 ohm resistor, which is red, red, black, brown, brown. The 220K, hold on a second, I gotta get out my tray. I didn't pull it out. Just to pause real quick. I had to go hunt for the 220K. That's red, red, yellow, gold. Okay, when you put the trimmer pot in, have the I guess you call it the trimmer screw, pointing east, I guess, this way. See what I mean? Okay. Your diode. Now, when you do the diode, to bend the wire so that the part of the diode that is the cathode, that's marked with a gray band, has the that wire, I should say, do it in such a way, there you go, that the cathode is buried and there's not a lot of wire sticking out, and the reason why is because that's it'll shock you pretty good. I mean, it's not going to do anything to you. It's just, it's a good zap. And so if somebody's holding it and they start touching around and stuff like that, if that part was exposed, or if they touch it from the bottom, they're going to get a zap. It's not going to kill you, but it's more like one of those little shockers that you made in high school. The NPN goes in. Come on, NPN, get in there, all right. 555 socket. We'll put the 5 in last, of course, just before we test. Okay. The 1K, which is brown, black, red, which is basically, so the brown is a get these confused. Anyway, the 10K is brown, black, orange. That is correct, and the 1K is brown, black, red, which would be a 1, a 0, and 2 zeros after that. That's the 1K going in here. The 10K here. And when we're done soldering this together, oh, I forgot an important part. What you want to do, take your razor knife, and you see this perforated edge, a perforated line right here. You want to separate. These two boards from each other. So just run a little razor edge on. Just score it a little. You don't really have to hit it that hard. And because it's perforated, come apart just like that. See, and this, put it away for later. You're going to want to solder the barrel connector on as well, so that we can apply power. When we've done that, we're going to apply power, and then we're going to measure between ground and this high voltage test point, which is right here, which I put in there. So we're and then I have a ground right here. So just between any ground and this high voltage test point, and then we're going to adjust the trimmer till we get to 180 volts, and that will be basically stage 1 of the clock done. And I'll talk about the rest of it. The rest of it is just parts falling into places. So hold on a second while I solder this all together now. Okay, it's all soldered together. I'm just going to do some snip ups, and then we'll check to make sure the power supply is working. Try not to put an eye out while I'm snipping these wires here. Let's see. Gotta get better glasses. Now the MOSFET, what I'll often do is align the hole like so, and then I will put a nut in there, or it actually isn't that necessary to put a nut in there as a heat sink, but you could just put a little solder down on this side and some solder on top, and I'll do that later. Oh hell, I'll do it right now. With the intention of just basically giving it more surface area, because I've got this pad to dispense the heat on both sides of the both sides here, and it just needs to be soldered into place. And so between the solder, that pad, and the heat sink that's already on there, there we go. It's all one part now. So you can see. I don't know why you can see that, but that's enough heat sink right there. So I should be able to put the 555 in, and it should, given the circuitry around it, oscillate and operate the trigger the MOSFET there, and which is then going to generate the high voltage, which we are going to adjust. I screwed that up. Hang on. Hold on just a second while I straighten these pins out. Okay, that embarrassing part is over. This is all fixed up. So now, set this to 200 volts. Find a 12 volt power supply in this bin of stuff. So yeah, this will do. Plug her in. Okay. I have that ground there on purpose. I have this high voltage here on purpose. It's at 37 volts. Now we adjust the trimmer. I don't know if you can see that. And we want to get it to 180 is the voltage I like for the tubes. 59, 61, come on. Okay, 80, 90, 100, 122. The tubes will light anywhere between 165 and like 200 and some volts. It's very low amperes, by the way, and it's just neon. 191. So I'd like to run them just a little below the rated for longevity, just below their rated voltage. 177, 178. We can adjust that later if we need to. So come on, 180. I'll take that. All right. So the high voltage circuit is done. Then what we're going to do next is same thing that I've already done on this board. No soldering's been done yet, but just populate all the resistors that go in there, all the other components that go. I can talk about why we're using optocouplers, which aren't on the board right now. The optocouplers are, if you're not familiar with them, you may want to read up on them, but they're separating the 5 volt part of the board from the 180 volt part of the board, and because this other LM7805 here, so we got 12 volts coming in, and you got the LM7805 is creating 5 volts, and that's what drives all the 5 volt side of the board, and then you got the MOSFET and this other circuitry that's creating 180, and that's going up to the tubes, but it's being gated right here. So this is basically the bridge point between the 5 volt and the 180, because what's happening is they're isolated, but the 5 volts are being triggered by the 5 volts are being triggered by the pins on the microcontroller, saying, you know, turn on, turn off, turn on, turn off, and in its isolated way, it's, you know, turning on and turning off the 180 volts. So that's a more unique way than I'm doing. I said more unique. This is a different way than I'm doing it than a lot of other people who just use high voltage transistors for their NIXIE clocks. I prefer it this way. Anyway, there you have it, and that's stage 1 out of the way. Okay, it's the next day. We're moving on to the next phase. I thought we'd break this up a little bit, and in this case, we're going to go to and we're going to install the 5 volt rail, and to do that, we're going to need the LM7805, and we're going to need, as a minimum with the LM7805, the two 16 volt 100 microfarad caps, and although it's not a hard requirement up to this point, we're also going to put in the 470 microfarad 25 volt cap, which really its purpose is to smooth out any noise on the 5-volt rail. So let's just put those in, and then once that's done, we can check for voltages and make sure they're doing what they're supposed to be doing. There's the 7805. Before I solder it, I'll line up these holes just like that. Again, the longer pin on the caps is the plus. You probably know that already. Let's see. Okay. All right, I'll get this soldered up. Give me a second here. Actually, you should probably hang on and watch this. With the pads on the smaller capacitors, they're very close together and they're very small. I could not design around that. So just be careful and slow, and that'll be fine. If you're going to accidentally make a bridge anywhere on this board, that's where it's going to be, on those these two caps right here. Okay, because they're just really tight together. And look, oh, that one's all crooked. We don't want it crooked, so let me rewarm that up and straighten that out. There you go. And it's just so hard to tell by eyeballing whether or not there's a bridge. So I'm going to use that. I think I did do a bridge. I think I fixed it. Okay. Anyway, I'm going to check that. Hang on a second. All right, soldered and snipped, and I just want to, before I apply power again, I just want to check, make sure I didn't make a bridge. I'm eyeballing, it looks good. Yeah, there's no connectivity between the two pins. That's good. And these two inside ones are both ground, so they should. Yep. All right. But yeah, if you're going to bridge it by accident, that's where it's going to happen. Again, with the heatsink, you could bolt it down. I actually made the hole big enough to fit a rivet, or you could just use a good amount of solder here. Get it nice and hot. Tons of solder. Squish it down while it cools off. And now the board, the heatsink, and the solder are all one, and see how it's got pads on the back as well. So you know that's dissipating the heat. I've been making these clocks for a long time, and that's plenty enough. All right, let's give it 5 volts and check the 5-volt. Good, 12 volts, and then check the 5-volt rail and make sure we've got 5 volt where we need 5 and 180 volts where we need 180. Alrighty. Set it on 200. They all share a common ground. I should make that really clear. If you look right here, that's just I put that there for convenience. That's a ground pin. And if you look right there at the corner of the 555 and in between the 555 and the diode, that's the pin for 180 volts. So you can measure with. But anyway, we're not. I mean, we can check for 180 right now. And am I not plugged in? Or do I have a short in the board? I believe I have just made a short in the board. Oh, I'm not plugged in. All right. Get that plugged into the socket. Give me a minute while I figure this out. Yeah, so the problem was exactly as I was explaining earlier. Be careful that you don't, when you're doing these caps, these pads are so close together that you just have to be careful not to bridge them. I bridged them. It was very, very small. I had to take a little razor blade between them to clean that up, but that's done. So anyway, you get your 12 volts in, and I use my convenient ground here. You can see we've got 100 and 80, just like we said it yesterday. And you go over to the LM7805. The middle one is ground, so ground to ground you're going to get nothing. This one here is the 5.3 volts coming out. Let's change that range down to 20. We get a more accurate reading. Looks like 5.3 volts. And then on the other side, this is the in, and that's the 1303, which is coming from my the 12 volt power supply. So we're good. We have power. Let's go ahead and check around here. Let's see, VCC 5.3. We're getting voltage where we need it. Let's see, the 18 mega power is I believe VCC is down here. Here we go. All right. Yeah, so we're getting power at the MCU. We're getting power where we need to get it, so you know, we should, because we know the board is good. One more place we can check for power is the positive side of the there you go. So it's all good. The power's, we got our 12 volt rail in, we got our 180 volt rail in. Next, geez, I guess we'll just go ahead and start putting parts in, because you got the 18 mega, you got this the crystal, you've got the two caps that go with the crystal, you've got another 470 microfarad cap. Again, it's there to smooth out any noise on the 5 volt rail. There's also decouplers for if there's any noise on the 5 volt rail. There's one for the 7141, which is a decoder, and the 18 mega. And then these are going to be your reset hours and minutes, each of them with a pull down resistor of 10K. Again, going back to your optocouplers right here, you've got 6 of them, 6 bulbs. We'll get that in. So I'll get all these parts in and soldered, and then we'll move on to the next thing. Hang on. I'm going to do these resistors next. Are 7, 8, 9, 10, 11, and 12 are 330s, 330 ohms. They're current limiters, so that we don't burn up the element in the optocouplers. And then the pull down, they're not labeled, but there's 1, 2, 3, 4, and 5, and yeah, just 5. 1, 2, 3, 4, 5. Looks like I pulled out 6. So let's see, 1, 2, 3, 4, 5. Only 5. 5 10Ks, because we used one of the 10Ks over there, and then we'll get those in real quick. All right, so you can see we've got the 330s in right here, and we've got all the 10Ks where they go, and these two 10Ks on the side are stacked vertically. All the other ones are either stacked flat or at a bit of an angle, just to keep them. There's different ones. I mean, if you get the 8th watt resistors, which would be just fine, they would fit in there perfectly. These are the 1/4 watt, so you know, they got to be either stood up or leaned over. They don't fit flush to the board. These do, however. So there you go. Moving on to, I guess I'll do the decouplers. I'll just put the final components in here, and then we'll move on to the bulbs. All right, so what we've got next is the 2 sockets. 2 of they're labeled 104. They're the decouplers. 1, 2, 3, 4, 5, 6 optocouplers, and let's see, we've got a set of a header with it's cut into 4 pins with 2 jumpers. We got a header that's cut to 6 pins. We have the 16 megahertz crystal and two 222 picofarad caps that are paired with that. 3 tactile buttons and 4 feet. I'll get those on. Okay, all that we talked about is soldered on. Oh, no, it is not. I didn't do the sockets, so I'll get those in a second. And in addition to everything I talked about, we're going to have to put these headers on, and this other header here. And this is the header that's going to be where the interfaces with the board. That interfaces with the board that has the tubes on it. It's going to go like that. So you'll see a male header and a female header, and then there's the female header. So that's how the two will mate up, and then we'll add the LEDs, the resistors, and the tubes last, and we'll be pretty darn close to done. In fact, that's really all there's going to be to it. So hang in there. I'm going to make a correction. What I said, one of these headers I said was 6. No, it's 5. It's 5 because you have the programmer header, which is 6, which is, here we go, which is 6 holes, which you'd only use if you were reprogramming the MCU, which I send pre-programmed. But if you ever wanted to upload your own code, this is where you would do it from. And then the 5 is needed for right here. Okay, and the purpose of that is where our clock, the RTC, the real-time clock, is going to go. And that is a it is, let me get one out here real quick. Well, basically, it's just a little timekeeper on a chip with a backup battery, and it will sit on top of those after they're soldered in. So hold on while I get that done. Okay, so the bottom board is assembled, and just plug the clock into those 5 pins right there. Put the feet in. We'll get an MCU, and then we'll get the decoder chip and plug those in. I'll get those. All right, so the decoder, some people call it a NIXIE driver. I call it a NIXIE driver decoder. The MCU, which is an Atmel 328, it's been pre-programmed with the code that I put together that drives this, and I think the paperwork I sent you gives a basic proof of explanation of how it works. I'm going to jump ahead really quick here and show you a completed board with the tubes on it, but don't worry, I'll go through the process of putting that in there. But I'm putting this on here just to test it and see what it does. See where we're at. Let's see, let's plug the baby in, and yeah, so we have a working clock. All right, so let's build this part. All right, to build out this board, we're going to need this header, 6 10K resistors, and one 330K resistor, and 2 LEDs. And when I built this board, I built it with the capability of running 4 LEDs, but I discovered pretty quickly that the 4 LEDs, which are in series, would draw too much current, and they'd actually be dim, and so I mean, so dim that they weren't really workable. So then I would just shorted 2 of these, and then I put a 1 LED in and bent it down, and that's always been the best way, and that works. That works the best. I'll show you how I do that. And the other thing I do is, because now they're too bright, I put a little bit of black magic marker on it, and it just gets them to like something that doesn't steal the it's the same, they burn the same color as the LEDs. It's a nice warm orange glow, but I don't want it taken away and being more interesting than the neon glow, and so I try to keep them as subdued as possible. So basically, oh, and again, with these LEDs, and it's not very well labeled on the board, but the longer pin, which is the anode, is here. So the longer pin is going in there. I suppose if you put it in backwards, it really wouldn't matter as long as the other one was in backwards as well, because they blink on and off, and high and low. So if something ever happened where they were both backwards, they would just blink opposite. But anyway, they'd be off when they should be on and on when they should be off. You seen how I bent them down like that? All right. Okay, and then what I'll do is on the back, I'll short those two sets of holes there, and that way you'll have these two in series. So there's that. I'll also put the 330 right here on the one called dim, and its purpose is to not burn those out by throwing too much current at them. The Arduino just can't seem to drive four diodes at once, but when you're doing two diodes at once, you still need to limit the current. So there you go. I'll get these R1 through 6, which are 10Ks. These are also current limiting, and their purpose is the 180 volts that is being routed to these neon bulbs. This limits the amount of current. This comes off the cathode, so and goes to ground. So it is hitting a resistor, which is limiting the amount of current that can actually flow through the bulb, keeping them from burning out. And some people, you can use anywhere between 7.5 to 20K, whatever. I'm happy with 10K. 10K seems to do the job. The bulbs on my clocks last for years. This clock, and you'll read about it in the manual, is multiplexed. What that means is only one bulb is actually on at a time, but through persistence of vision, it looks like they're all on at the same time. It's called multiplexing. So hang in there. I'll get all these things soldered on, and then we'll test and make sure these things blink nice. I'll put a little black magic marker on them, and then we'll put all 6 of these NIXIE tubes in there. So there's that. Looking pretty good. Remember how I said I want to short these 2 in the back so you can still have these things in series? What I like to do is use the LEDs extra wires here, because they're a little thicker than the other wires we have laying around. And what I also do is I loop them over, basically just like make a U, send it back in, but I let that U stick out like that. You see that right there? I let it stick out a little, and the reason why I do that is as many of these as I sold, people would email me back and say, hey, can you make it so the lights don't blink, because I keep it next to my bed and it's it's annoying. So the solution's real easy. See that? I say, see that little loop in the back? Just snip it, and when you do that, they're no longer in series. There's they're off the. So all you got to do is snip one of these 2. They're just back there, nice and tidy. You can bend them down like this if you want. See the loops right there, there and there. They're just there to, in case you decide you don't want them to blink. And all you got to do then is just snip that. But you know, let's see, get these extra little bits of wire off of here. All right, and then before we do the bulbs, because they are the far and away the most expensive part of this thing, and you don't put them on until you know everything's working good. Plug it in, turn it on. We should see some blinking. Yep, there, blink. All right, and it went through its test routine. And then it should start blinking once every when it gets going. It's okay. There you go. On, off, right? Okay. So that's good. But what I like to do is take a black magic. Hot. Sorry. Take a black magic marker and just put that over these. A minute ago, I put my finger right on that heat sink right there. Okay, come on. Yeah, that'll do it. Check it one more time. Self-test. Now it's testing each bulb. You'll see that when we're on. Okay, here we go. Blink on, blink off. Every second. Okay, we're going to do the bulbs next. Let me go get them. I like to think of this as a board with a lot of cheap Chinese parts and some expensive Ukrainian parts. So this box, date code on this box is December of 1990. Let's say Ukrainian. Actually, I think they're Russian parts. Back in those days, I don't think people really knew the difference. So let's just take 6 bulbs out. And these bulbs are just getting rarer than hen's teeth, which is one of the reasons I don't make these clocks anymore. All right, and what you want to do what we're going to do is we're going to mount. The board is the socket, so we're going to mount the tube into the board, and the tension is actually good enough for testing, so you don't have to solder the socket just yet. So just insert the tube into the board, paying attention to what's up and what's down, and yeah, again, the board is the socket. But once we're satisfied that the clock works and that the tubes are all functioning, because you could have one with a bad element in it, and it happens. A good, maybe 1 in every 20 of these is something wrong with it. So you've got to test. You don't want to solder it in place. It's just a pain in the ass to unsolder it. So so just test it with the tubes loosely. Actually, it's pretty tight. Okay, so now you've got your tubes in, and they are currently unsoldered, but they're in and they're making contact. And I mean, they're in. If you look, they're in nice and tight. They're not coming out. But I always solder them, because you don't have to, but I solder them because these things would go to get shipped, and they could come loose during shipping, and then I'd get complaints about I was afraid I would get complaints about how, hey, it came loose during shipping, you sent me a broke clock, when the clock wasn't broke, it was just shipped badly. So anyway, we have it like this. Again, let's find the power supply. Turn it around so you can see it. And let's take a look. Okay, self-test. All right. So we're not, the bulbs did not do what they were supposed to do. So I would guess that means they're not getting power because they can't all be not grounded. So let me see what's up with that. Alright, so here's an interesting thing. All the tubes are working except for one where everything is working, which means it's on it's on all the time when it shouldn't be. This guy right here. So what that's telling me is the optocoupler is no good because it's basically stuck in the on position when it shouldn't be. So I'm going to go back and replace that optocoupler and see what the deal is. But here, that is a good example of what could go wrong. So hang on. Well, I figured it out. What fried the it's fixed now. What fried the that one optocoupler along with it actually wound up frying this chip right here too. But what it was I had again a bridge in the back of this board, right about, I don't know, right there, and it was actually shorting one of the logic lines. Anyway, so that's you know, I guess I'm out of practice because I've never made that mistake before. I have accidentally bridged this before, like I did earlier, so that wasn't a surprise, but I've never made that mistake before. So anyway, lesson learned, and in the process of troubleshooting, I burned up 3 of these chips. They're about $1 each. So anyway, lesson learned. I guess it was a cheap lesson. But here, let's test it out. It's perfect. So, I guess you, oh yeah. So, you'll notice the bulbs are working, but you know some of the lights aren't. Okay, like you notice this one when it got, okay, sorry, this one here, it's missing the digit wasn't there. I think that was the 3, and I'm not surprised because we haven't soldered. It's just sitting in the socket. Here we go. If I was to push it around a little, let's see if the 3 works now. 0, 1. No, now the 2 and the 3 both don't work. So I'm going to go ahead and solder these in place. I know they work. It's just they're not making contact well enough in the back here. But they did test well. So I'm going to solder those. And before I do that, I got to make sure they're lined up nice and straight. Because once you solder them in place, once they're soldered in place, they're not going anywhere. And you don't want a crooked one. I mean, you know, this isn't precision, but you want to make sure that they're nice and straight, and if none of them are crooked, or if they are crooked, they're crooked in the way you want them to be. I mean, because after all, these things are molded glass and all that, so with the pins coming out, so the pins do what they want to do. All right, I'm going to flip it over. I'm going to solder all these babies on. And we will have a complete working clock. Now we can talk about multiplexing here real quick. Again, only one tube is actually on at a time, and that's why when you look at it while I'm filming, sometimes it might look like it's blinking. Well, it is, but your eyes can't tell when you're looking at it because it's multiplex. So if there's 6 bulbs and it's multiplex, that means they have a duty cycle of 1/6. That's a good thing because you get 6 times the life out of the bulb, theoretically, because it's not burning constantly like a direct driven NIXIE clock would be. So the advantages to multiplexing is you need less components, and you can drive the multiplexing in software, and the disadvantage is you have to drive the multiplexing in software, so which to me is no big deal. I don't think And many of many things. I mean, you know, your pocket calculators, the old ones in the old days, they were multiplexed because you didn't want to have a chip, a decoder chip for every single digit. It was just be wasteful. And all right, so they're all soldered in place. Make sure the three and the just, yeah. So we've got, you know, one way to guarantee a good contact is to use solder. Yeah, there we go, more business. So you've got